We have welcome Manish Jain here. I was wondering if we had any representation from Australia, and we actually do. So he is the co-founder of Dgraph, and he's been in Google for about 6.5 years, organizes the Go Meetup in Australia, and loves to travel the world, lived in 5 different countries before he was 30 years old. So let's not ask him how old he is right now. He loves to travel ultra light, and people don't believe him when he travels really light. Let's see how light we can get with your talk.
All right.
All the best.
Thanks. Hi, guys. I'm Manish. I'm here to talk about Dgraph, which is a graph database for production environment. Here's the agenda, what it's going to look like. We're going to talk about introduction, show you quickly the benchmarks. We'll talk about the design of Dgraph, our opinions on Go after having used it. I've used it for the last 3 years, and we've used it in Dgraph for over a year. I'll give you a demo of Dgraph, and then finally, if we have some time, we'll go over questions. Hi, Diggie. Say hello to our mascot, Diggie. He's a badger, and for people who know the context or have seen the video, he's a badass and does not give a bleep. Why badger? Because they like to dig. And at Dgraph, we like to dig data. So before I jump into Dgraph, let's talk about graph databases. What are graph databases? Graph databases are databases optimized for handling graph data. Duh. In addition to property lookups, common with both relational and key value store, graph data frequently requires users to traverse edges or relationships, also known as joins. Therefore, graph databases optimize for both lookups and edge traversals. People have this misconception that graph databases are only about edge traversals, but they must do lookups. So a good graph database would do both equally well. Doing joins is a first-class citizen action for graph databases. Here's a Gorilla question. When should you use a graph database? Everybody has heard about a graph database, and they have no idea when to use it. So I'm going to give you my opinion. I think if you are using a relational database and you have more than 5 interconnected tables, that's a good use case for a graph database. Now think about it for a minute. I've seen database schemas which just go completely connected, and they're still on SQL. Next time you see that, think about using some graph database. They're ideal for news feeds, recommendation engines, context-based searches, pattern and fraud detection. They have been used in terrorism detection. In fact, UK Security Department released their graph database 2 years ago. So they are being used. What is Dgraph? Dgraph is an open source graph database built for web-scale production environment, written entirely in Go. In fact, the reasoning behind why I started Dgraph was I was working at Knowledge Graph at Google, and over there we had to serve the entire knowledge graph just behind web search. So we needed something which would scale well. So that's what inspired me to start Dgraph, because I realized there's nothing outside which was like that. Dgraph is sharded and distributed. That means we do distributed joins, distributed filters, and distributed sorts. It's horizontally scalable. It does automatic replication. We are consistent. That means we choose CP in the CAP theorem, C for consistency. That means in case of a network partition, we'll choose consistency over availability. Having said that, we are highly available by design. A lot of people mix the two. CAP theorem is specifically about a network partition, but a system can be highly available. So Dgraph has no single point of failure, and it does automatic failover in case of machine crashes. And finally, we are fault tolerant. That means we can handle server losses without affecting queries. The system can even be partially available for subset of data. So that's a bit about Dgraph. Why build it? Graph databases, graph technology is hidden, but it's everywhere. I think any company doing anything smart is using graphs. But there are no native scalable solutions. Existing graphs are either single server architecture, like Neo4j, which can only vertically scale up. There's no sharding. Or they are graph layers on top of other databases, like Kali, which a lot of people are familiar with. A lot of Go community is familiar with that, or TitanDB. So with no existing standards, companies have to build their own graph systems to deal with graph data. For example, we have Facebook Tau, Google Knowledge Graph, Twitter FlockDB, and Dropbox and Pinterest are building their own, and there's numerous others. Therefore, we're building Dgraph with the aim to provide a fast and horizontally scalable graph database, which can work for large and small companies alike. So let's quickly just look at some benchmarks. All right. Let me see if well, there's no interconnection for me, but I was going to show you a video about reloading data against Neo4j. We have a 1.1 million RDF data set that we picked up from Freebase film data that we loaded with Dgraph, and at the same time we loaded with Neo4j. And Dgraph was giving around 50,000 RDFs loaded per second. Neo4j was doing around 200. When the slides come out, you'll see a link to YouTube video that you can see. So we are at least 100 times faster compared to Neo4j. And there's a good reason for that. Neo4j acquires a global mutex lock around every transaction. Every read, every write has to go through a global mutex lock. But the way Dgraph design works, it's highly concurrent. So we acquire logs at a very granular level, and we use Go routines very heavily. So that helps us be very concurrent about both of our writes and reads. In terms of querying, Dgraph is 3 to 6 times faster on a read-write workload, and at least as fast as Neo4j on a read-only workload. And currently, we don't do any caching, but if we start doing caching, this would only improve. There's a link to our benchmark code in case you want to independently verify these benchmarks. It's open source. Then we did this comparison in Kali. We ran Kali with BoltDB on a MacBook. And Kali, as I explained, is a graph layer built in Go, also by another Googler, ex-Googler. We loaded 21 million RDFs using the same Freebase film data, and Dgraph was around 10 times faster. We ran queries using Gremlin for Kali, and Dgraph was 37 times faster. And then we ran Mequal for Kali, and Dgraph was 5 times faster. Same thing, there's a link to it. All right. So design. Let's look at the design concepts for Dgraph. The smallest data is an N-quad. It's what we call an N-quad. It's a standard by RDF, which is a subject predicate object, sometimes along with language and label. Objects can be entities, for example, friend relationships, which will point to an entity, or they can be values like date of birth. Dgraph assigns a uint64 integer to each entity to save space. And there is significant space savings because of this. We group N-quads by subject, predicate to create a posting list. The posting list keeps the object sorted by ID. And that's very useful when we need to do intersections, because you have two sorted integer lists. Doing intersection is an ON job. We then group all the posting lists for the same predicate as a shard. Thus, there is one shard per predicate. The same, we combine multiple shards into a group, and how this grouping is done is configurable by the end user. Groups can be assigned to servers. In general, multiple groups can be run by each server. As you can see over here, we have 3 servers, and each server can run arbitrary number of groups. So somebody runs 2, somebody runs 1, somebody runs 4. And the same group can be assigned to multiple servers to allow for consistent replication and availability. So in this same case, in case server number 3 crashes, group G1 will continue to write the data and read from the data. The user would not even know about it. You ideally want 1, 3, or 5 servers handling a group because you need odd number for consensus. We're using a consensus algorithm called Raft, done by CoreOS guys. Now let's look at how the data flows through the system. So, can you guys see a mouse here at all? Say yes if you see mouse. All right, awesome. So I'm going to just point to things so it makes it easier to understand where am I. So each query from the client can contain many edges. This is the client, and you have a query. It's a batch query. And any server in Dgraph can receive this query. It would determine groups handling each predicate shard and group the query accordingly. Then it sends each query group to any server handling that group. So it can send it to this, send it to this, send it to this, or send it to this guy. On receive, the peer would sync the update to disk using a write-ahead log. This would persist data before it. This will persist data through server crashes. It's a sync to disk, so it gets pushed all the way down. Raft would then achieve consensus among peers. And once consensus is achieved, each entry in the batch is applied to the posting list. The application is done in memory first, and then it's synced to disk later. This is very useful because if the same posting list has a lot of updates, then you don't need to read from the disk, upload in memory, write, and write back to disk. So you avoid all that. You just read from the disk once, you apply all the updates, and then you write it to disk eventually. So this avoids disk thrashing. And we don't need to worry about data loss because we already have the write-ahead log, which is already synced to disk. Once everything is applied, a reply is sent back to the client with errors, if any. So this particular server would block until this whole step has happened, and then reply back with any error. So despite the serialization done by Raft here, the writes are concurrent and really efficient. We're able to do close to 75,000 enquads per second on a ThinkPad. So this is how we do writes. What's our consistency model? Sorry, I forgot to do this. We do atomic consistency, also known as linearizability. Without showing a full diagram and without going into details, just know that reads after a successful write are guaranteed to return that or any future write, irrespective of which replica is queried. That's a property given to us with the write application of Raft. Now let's look at how data is queried, or how we solve the problem of distributed joins, distributed filters, and distributed sorts efficiently. If you think about a Dgraph query, which is a graph query, it's a tree-like structure. Each branch is handled by one go routine, which allows concurrent execution of sibling branches. You can't execute the children concurrently, but anybody at your level, you can execute concurrently. Let's look at the life of a branch. There are 5 stages to it. The first one is to expand. So we take a list of entity UIDs and an attribute / predicate. It's the same term for the predicate. And send it off to the server handling that attribute. The server then looks up attribute, UID pair for all the UIDs in the list and returns back a UID matrix. That is lists of UID list. For example, if you look at this, you want to find friends of ABCD. So you send it to the server which is handling the friend predicate, and it gives you back the friends of A, friends of B, friends of C, and friends of D. D, unfortunately, has no friends. So that's how we do expansion. Then we do filtering. So we merge the UID matrix that we had received from before. This is the UID matrix I was talking about. We merge it into a UID list. And then we repeat the expansion process for filters, this time using filter attributes. So you might be filtering by, let's say, date of birth. So we'll send it to the server. which contains the predicate date of birth, and expand on that. Each branch of the filter tree would intersect or merge the results as per the instruction. Once we receive the final results, we filter the original UIDs list using this. So we now get a filtered UID list. Not all of these are actually like Go routines as well. Then we apply sorting and pagination. To sort by some attribute, we send this filtered UID list to the server handling that attribute. This is the same thing as we did in 2 previous steps as well, right? But the difference is this. Sorting is done based on the values of the attribute. But to avoid having to retrieve the values of all the query UIDs, we pre-group all the repository UIDs by attribute equals to value keys. This is the index. This is what we call indexing at Dgraph, to generate these attribute equals to value keys for sorting. So think of this like a bucket sort. So now what we need to do is we just intersect the source UID list with the UIDs in the bucket. And as I said before, these intersections are really fast because they are all sorted. And continue doing this until we reach the desired number of results. So we start from, if we want to do ascending sort, we start from the first key. We get the number of results. We are like, this is still lower than what I need. Go to the next bucket, go to the next bucket, go to the next bucket. Okay, I received enough results. This is how you might do, for example, top 100 movies by IMDb rating. And now for this limited set of results, we retrieve the actual values for the attribute to do a slice sort, exact sort. And this is the final result which gets returned. Now, for processing children, we just continue the same thing. We go to the children branches, and we do the same process recursively. They might also have filters, they might also have sorts, etc. And finally, when all the branches are processed, we convert from this attribute-based queries and results to UID-based nodes, encoding them to JSON or to Proto as requested. So why do we even do this? Why do we do this predicate-based thing before? Because in a distributed system, the best thing you can do is to decrease the number of network calls that you need to make. So that's what we do over here. I'm quickly going to show you the life of a query with an example. We want to find all the movies by Steven Spielberg named Indiana, sorted in descending order. So this is the ID of Steven Spielberg. We first expand out director.film edge. We go to the server, which is director.film expanded out. Then we apply the filter by going to the server which contains name.en. There must be an index there which is called Indiana, which would have a list of all the UIDs for Indiana. So we intersect the result we got from director.film with the UID list of Indiana. This gives us the movies by Steven Spielberg with the name Indiana in them. Then we sort based upon initial release date. So we send to the server which contains the initial release date predicate. We apply the sorting over there. Then finally, we process the children by doing recursiveness. And then we convert it to JSON, which gives us the 4 movies by Steven Spielberg, all the Indiana Jones movies. And if you look carefully, these are sorted by date in reverse order. All right. So what are our opinions on Go? Things we like about Go. Simplicity of code. Dgraph is a complicated piece of technology. Go helps keep our code base simple, readable, and maintainable, and lets us iterate fast on the code base. Concurrency. Dgraph uses Go routines very heavily for both mutations and query execution. Thanks to Go routines, we are able to use all the cores of server close to 100%. Profiling via pprof. If anyone has ever done any latency improvement work, they realize how important it is to have a good profiler. Go profiler helps us detect any slowdown in Dgraph, so we can keep Dgraph fast. In fact, if we look at Dgraph running, the top 20 things that a profiler would show, Dgraph would not be in any of them. Any of Dgraph code would not be in them. Benchmarks. Benchmark is a quick way to settle disputes among team members. It becomes really easy to prove or disprove assertions and get the thing done. RPC tracing in a distributed system with lots of query flowing. RPC level tracing is the only way to get logs and use them productively. Advanced memory management. Dgraph puts a lot of pressure on memory, which then puts a lot of pressure on Go garbage collector. So we avoid allocating on heap as much as we can, and then reuse memory as much as we can. The good thing is, as opposed to other GC languages, Go makes this possible to play with pointers. Go format. Go format is my favorite. It's habit forming. Once you get used to Go format, which takes less than a day, things look weird when code doesn't automatically format on save. So I can't ever go back to JavaScript. Go compiler is fast, right? Everybody knows that. But here's the biggest thing about Go compiler and static checking in general: refactoring. We can refactor code faster than we can add hacks on top of existing code. By the time our code compiles, it works. And that's really useful. So what are the things which are pushing us away from Go? I think lack of good library support is the biggest thing affecting Go development. Having to use CGO due to lack of good library support is really bad. For example, for indexing, we wanted to support Chinese, Japanese, Korean, and there is no Go library which can tokenize CJK languages. So we ended up having to use ICU library written in C++ via CGO, and that is the slowest piece of code we have. Similarly, a well-designed, concurrent, high-throughput read-writes key value store is currently not available in Go. So the best bet that you have is to use RocksDB via CGO. And that's where profiling stops working, memory starts leaking, and hell breaks loose. So what do we do about it? We are planning to remove CGO completely from Dgraph. Having to use library via CGO is like having to drive on a congested highway on your way to office every day. You can either pay the penalty of it every day and keep doing your job, or you leave your job and dig tunnels underneath, like Elon Musk does. In Go world, that means building a library from scratch in Go. In fact, I decided to take some time off writing code for Dgraph and build a performant key value store as an alternative to RocksDB in Go. The work is underway. We plan to release it in version 0.8. We're also removing our CGO-based ICU tokenizer and planning to reuse parts of Believe. What we lose in CJK support, we are going to gain in Go-gettable Dgraph. Finally, I have a demo of Dgraph. This timer shows 2:50. How much time do we have left? We have. All right, so I'm going to show you a demo of Dgraph. Okay, so we ran Dgraph over here. Okay. Let me. Okay, let me show you this query. So in this query, what we're trying to do is we want to find any entity whose name contains any of Spielberg, Nolan, or Tarantino. People in the back, can you guys read this? Just raise your hands. You can read it, yeah? All right. So we want to find any of Spielberg, Nolan, or Tarantino. And then what we want to do is we want to find their name. Now this director thing over here, this is just an alias. So instead of saying name.en, it's going to say director. Okay? Let's run this thing. All right. So now we have a lot of Nolans, a lot of Tarantinos, and we even have film festivals. Now that's not exactly what we wanted, right? We wanted to know about the directors. So let me modify the query a bit more. I'm going to add a filter, so we are only picking entities who have directed at least 10 movies, right? So what I do a count of director.film, which is the edge which goes from an entity to the film. So if this person has directed any movie, it gives me a count of that. And then I say greater than, which is greater than 10 in this case. And then I filter it by that, right? So I want to filter if they have done more than at least 10 movies. And you can ignore this normalize for now. It's just a way to make the result look better. And also, we want to get the count, right? So we know that the result is accurate. All right, that looks more like it. Steven Spielberg did 39 movies, Tarantino did 17, Christopher Nolan did 11. Okay, so that's our directors. Now let's make it even more interesting. Okay, so we have the same filter. We have the same filter over here. Now in this case, we just want to get the films by these directors, right? So inside the director, we just add director.film, which is the edge going from director to the film, and we get the name of the film, right? So again, I have an alias just to make it clear. Okay, so now we have Steven Spielberg. Steven Spielberg, a bunch of movies by him. Quentin Tarantino, Kill Bill, Pulp Fiction. William Nolan, this guy I don't know. Christopher Nolan, Dark Knight Rises, Interstellar, etc. Right? Okay. Now let's do a bit more. And what we want to do is, we only want the movies which were released in the 1990s. Okay? So we got the, if you see before, right, we had director.film, right? So what we're going to do is, in the director.film, I'm just going to add a filter over here, greater than 1990 and less than 2000. Okay? And also we want the initial release date, so we know that the results are correct. All right. So we have Steven Spielberg, Saving Private Ryan, 1998, Jurassic Park, etc. And then we have Hook, and we have Schindler's List. But the results look a bit weird because they're not sorted. But I'm just going to show you quickly. So we have everything is 1990s. William Nolan did not do any movie in 1990s. But as I said, the results are like, they don't look very clean. So what we're going to do is, all of this remains the same. We're just going to order by the initial release date in descending order. So that's Q5. Okay, so we have 1998, 1997, 1997, 1993, 1993, 1991. And just be careful, right? I mean, because this one actually does the sorting by the date, right? So you do see, 1997 twice, but it's sorted then by months, and then finally by the actual day. So Tarantino did a few movies, Reservoir Dogs and Pulp Fiction, again sorted. Christopher Nolan did too. Okay, now let's make it even more complex. I'm going to go, so this one is the same mostly. We still have the director. We still have the filter on the directors. Then we have filter on the initial release date. I did one change. I changed it to 2015 just to get a bit more results. Okay, now let's look what's up. So this is what we call a var block. A var block is useful to introduce variables in the queries, right? So in this case, what we say is we say, hey, give me any entities whose names is Hanks or Pitt or Damon or DiCaprio, right? Find the movies that they acted in, and the way Freebase film data stores this is it 2 edges out. So from the entity, you go to actor.film, intermediate node, and from that you go to performance.film, which is the actual film, right? So we need to go 2 edges out, and we store these films as F, right? And in the director.film, we filter by identity. As most people know what identity means. We filter by IDF, including the filters on the initial release dates. Right? The rest is the same. Okay, let's try this. Okay, so we get some results, right? Steven Spielberg, The Terminal, Catch Me If You Can, Django Unchained, Inglourious Basterds. They look like they are the right results, but we don't know because we don't see who is the one who acted in these movies. So let's modify our query a bit more. And we go to 7. In this one, we have the same block, but we also store the results from here as A, which means actors, right? So A as actors. We store this as A. We still get the same films, but then we also get the actors. And same way, from film to actor, you have to go 2 edges out. So you have to go from film to starring to performance actor. But then what we do is we filter by identity A. So we only want those actors that was up in the var block. Let's try this. Okay, now that looks interesting. Steven Spielberg did Indiana Jones, and the actor name is Chet Hanks. He did The Terminal. Actor name is Tom Hanks. Catch Me If You Can, Tom Hanks, and Leonardo DiCaprio. Saving Private Ryan is Tom Hanks and Matt Damon, right? We have Django Unchained, Leonardo DiCaprio, Inglourious Basterds, Brad Pitt, so on and so forth, right? So this is nice, and it's great for me because I'm a backend engineer and I like to see everything on Bash, on Terminal. But some people like to see things in better screen. So let me see if I can run this query over here. Okay, so this is the same query as what we have there. Right? And I'm just going to run it. So it gives you the 3 directors, Christopher Nolan, Tarantino, Steven Spielberg. Let me expand that. Right? Now what we're going to say is just going to expand the button. And it shows you all the actors that you might have. Let's just move them a bit over here. So we have Django Unchained, point to Leonardo DiCaprio. Inception is also the same. Christopher Nolan is here. Steven Spielberg is over here. Saving Private Ryan points to Tom Hanks, which also goes to Catch Me If You Can, etc., etc. So it's a good way to visualize the results and the things like, it's a pretty cool library. Yeah, so that's how graphs work. Let's go back to, cool. If you want to try it out, it's a very simple command. You can just run this command and it would install on a machine and you can start working with Dgraph. Finally, if you have some questions, how much time do you have for questions? No? We probably don't have much time for questions, but find me and the Dgraph team. Hey guys, introduce yourselves. That's the Dgraph team sitting right over there. There's going to be a tea break right now, so find us for questions. Knock at our doors. We are staying at the Hyatt just upstairs. And we got some freshly printed T-shirts right on that desk. So just come and take them. Thank you.